Hello, and welcome to Sizing and Selecting Heat Pumps in Colorado. This is part 2 of a free heat pump training series that the Center for Energy and Environment has put together in partnership with Energy Smart Colorado, Xcel Energy, La Plata Electrical Association, PRPA's Efficiency Works programs, Holy Cross Energy, and the Beneficial Electrification League of Colorado, or BELCO. Just to make sure this goes well and to reduce the overall size of this, I'm going to turn off my camera for the bulk of this, but we wanted to say thank you very much for joining us, and we'll jump right in. Now, whether you were with us for part 1 of this, the load calculations for heat pumps, or you're just joining us now for the first time for this one, you'll notice that I am Dan Wildenhouse. I'm the Senior Technical Manager and Trainer for the Center for Energy and Environment. I'm a recovering contractor. I spent 15 years as a contractor doing HVAC and weatherization and low-rise multifamily, small business, and residential settings in both new construction and existing buildings. You can see me there in my pro mustache phase. It varies depending on what time of the year you run into me. The last 15 years I've been working as a consultant and a trainer, primarily for utilities and local governments, but I've also worked for a few community colleges during that time. And I am a Colorado resident, so I bring to you not just 30 years of experience, but years of experience and time spent working in and now living in Colorado. So what exactly will we cover today? Well, the first couple of parts, why right sizing matters and load calcs, just a quick review from what we went over in the first version of this. So for those of you who did not attend the first one, that's okay. You can still go back and watch it at your leisure, but we'll just give you that quick review. Then we'll jump in. We'll start talking about specifications, because specifications are going to matter when we start thinking about how do we size and select a system. For instance, can you think right now about whether or not a cold climate system will be sized for heating or sized for cooling most often? How about a non-cold climate system, right? So that's part of what we'll cover. We'll talk about the design phase overall, manual S and its alternatives. We'll get into some specific options, some challenges we see in cold climates like Colorado, where the heating load is 1.5 or 1.75 or 2 times the cooling load in the state. So how do we address that? How do we design systems that are the right size for one load and not dramatically oversized or undersized for the other load? We'll talk about altitude and dry climate adjustments, and then a sizing for ductwork short piece. Typically that is its own long session, but for today we're going to give you a short burst on sizing for ductwork. So the problem statement. Sizing and design and selection, it's often done just based off of some simple rules of thumb or based on what's already been in the house. Now here's a statistic for you. I was able to see the statistic grow in live time when I worked on a program in the Pacific Northwest. And by that I mean I was there when they actually did the survey of homeowners and found that 2/3 of people are somewhat or currently unhappy with their existing system. So let's think about that. 2/3 of the people that you encounter as a contractor are already unhappy or somewhat unhappy with their existing system. So why would we size something and put in the same exact size piece of equipment if there are opportunities to solve those problems? Now that study was done in the Pacific Northwest, but there have been other studies around the country that have given similar answers, that more than half, almost no matter where you are, of people are either somewhat or fully unsatisfied with their current system. The reason this problem statement matters is because variable capacity heat pumps are going to perform their best, and they're going to meet those savings goals that both the utilities and the homeowners want when they're sized appropriately for the system type, for the application, and the supplemental or backup fuel type. So sizing a system when you have natural gas as backup could be quite a bit different than sizing a system when you have propane or electric resistance as backup. This is specifically what we hope to address in today's portion after we do that little bit of review on load calcs. So some folks are concerned that load calculations need to be padded, right? They're afraid that if they do not add a little extra oomph to what the building says it needs, that they will have callbacks because the system won't be able to deliver. This is a study that we did, I believe, in 2017 at Center for Energy and Environment. This was not the number one part of the study. This was a secondary component of it. We were looking at boilers. And we had contractor A and contractor B each performing load calculations on the sites that were included in our study. We also were monitoring and measuring the actual energy use during the colder times and warmer times of the year in order to kind of look and see how did the load calculations compare to what we actually saw happening in the house. For each of the sites, you're going to see 3 bars. The one on the left is the modeled, or not sorry, the monitored and measured actual energy use versus the loads that were calculated using Manual J software by contractor A and contractor B. Now you're going to notice 2 things right off the bat. Contractor A and contractor B rarely agreed exactly what the load was, but that's okay because more often than not, they would have recommended the same size piece of equipment, meaning that just because one said it required 40,000 BTUs, the other said 47,000 BTUs, the answer they probably would have recommended was 48,000 BTUs because that is the size of equipment, right? It comes in 12,000 increments. But the fact is that they did get different answers. We also saw that contractor A, the middle bar, more often than not, had a higher load than did contractor B. Now, as a part of our study, we did not look into what software they used. We did not look at what assumptions they made. So this was just some raw results. But where it gets really interesting is even if I only look at the larger loads in this study, so the ones to the right half, right, where the measured and monitored loads were higher, even there we still saw quite a bit of discrepancy in most homes between the modeled, which was the Manual J, and the monitored and measured. Sometimes it was almost double the modeled load was. Other times it was actually pretty close. If you look at site 1031 and 1045, those are pretty close answers. But site 1052 and 1070 and 1054, on the other hand, the modeled loads were much higher. So what does this tell us? It tells us that there's enough padding built into the software that it will more than enough take care of what's actually needed for the home. In other words, there's no reason to either mess with the model to get it to say a higher number, or to then take those results and oversize and select a piece of equipment dramatically larger than the load, because there's enough buffer built in already. In fact, ACCA themselves, the ones who determine whether something or not qualifies for their Manual J standard, even ACCA says that there is no need to pad or manufacture a higher load on the building in order to protect yourself. This stuff is already built in. So does sizing really matter? Well, there's a lot of different ways you can ask this question. One of the biggest ways I'm asked is, does it really matter in terms of energy penalty or energy cost? So when we look at this, we see if it's oversized by cooling by more than 140%, so it's more than 40% over, we do see some energy penalty. Some energy increases are there. Now, the energy increases are somewhere in the 3 to 9% range on the cooling side when you're oversized. Some of that has to do with oversized systems stop and start pretty routinely, and that is not the most efficient time of their use. You can also have issues where the compressor itself is really challenged when it's oversized, and so that can have a small penalty. On the heating side of the equation, similar results, somewhere between probably I think 1 to 7%. If you're oversized by more than that 50%, so if you're 150% of the load or more. So you do see some small energy penalty at the compressor, but where we see the big impact is being wrong size for the ductwork, because this can lead to a much higher fan watt draw, particularly for ECM fans. Now, ECM fans are usually going to be found in either high efficiency systems pre-2017, a mix of systems between 2017 and 2019, and almost every system after 2019. And the reason why is around 2017, the federal minimum standards, so this is the Department of Energy and others in the federal government who set the standards came out and said, at this point, all manufacturing must meet ECM fan motors in our central air handlers. But they gave, I believe, 18 months to 2 years for distributors and manufacturers to sell off the product they had already made. So even though the rules changed in 2017, the sell-by date was in 2019. So that's why I kind of put it that way. But when you see an ECM fan motor, you will actually be able to continue to push past a lot of resistance. They're great at delivering air, and they can be really efficient when there's not a lot of high static pressure or resistance built into the ductwork. When there is, you can see the fan energy use go up fairly dramatically to try to overcome that resistance. And that's where we see this increased fan power draw, up to almost 50%. So that means a fan that was supposed to use 300 watts to blow 1200 CFM throughout the house may end up using 450 watts if there's a high static pressure. So the energy penalties, yes, there's likely some if you're very oversized for cooling or heating at the compressor, but it's much more likely the fan watt draw will be what's impacted by this. So this will add up over time, so it is important to understand. There are a great many other reasons, though, why we care about this, other real-world challenges that have to do with oversizing. I don't want to spend as much time on this because we spent a lot of time on this in the first seminar, but we'll go through them here. For filtration, so if you have a improved filter system on your central air handler, maybe because of wood smoke, or you're in a construction area, or you're near a freeway, or maybe it's just because since the pandemic, you realize you spend a lot of time in your house and you want to filter as much bad stuff out of the air as possible. Well, if you want to filter stuff out of the air, you have to have air moving through the filter. So the length of the runtime will matter if you actually want that filtration to happen. The same thing happens if you have ventilation integrated in with your central air handler. If you want that to make it work, the air handler actually has to be running. And this could be true whether you have ductwork that is connected directly to your central duct system, or if you have a completely separate system, but it is synced through its controls to come on at the same time as your central air handler. Without the runtime, you're not getting the ventilation you think you are. For home destratification, runtimes matter. We've all been in that house where during the summer it's 7 degrees hotter upstairs than it is on the main floor, and in the winter it's 8 degrees colder in the basement. If we want to destratify that, we do that by moving air throughout the building on a very regular basis. And that helps us get more like a 2 or 3 degree temperature difference, or 2 to 4 degrees instead of 6 to 8 degrees. And that little amount can dramatically help people feel more comfortable in their homes. On and off systems can have larger temperature swings. The system overshoots past the thermostat set point, turns off, drifts down and begins to cool in the house or heat up depending on your season, and then re-engages, and you have a swing by 2 to 4 degrees on either side of the thermostat with some of these oversized systems. That allows for, again, a lot of disparity and delta between the peak and the valley in terms of how much heat is being provided. We want to avoid that. We want longer runs with less on and off. If we're trying to humidify in our homes, whether we have a central steam-driven humidifier integrated in with our system, or we've got separate ones. Maybe we have a humidifier and a couple stand-up Energy Star ones in a couple places in the house. Either way, if you want that humidity to be distributed throughout the house in Colorado, you need to have this runtime. These larger compressors and larger fans may require larger electrical circuits. If you're at all concerned about the need to upgrade the electric panel or any other electrical components in the home due to electrification or adopting heat pumps, you run that risk greater with the larger compressors and larger fans. So in order to, one way to help not have to do that is to right size the equipment to ensure that it's going to do its job without being oversized. These larger compressors and fans can be noisier as well. Believe it or not, noise is a component of indoor environmental quality, just as is comfort and indoor air quality. So IAQ, comfort, and sound are all part of IEQ. Now, it's not just what's happening inside the house. What's happening outside the house matters as well. If you wind up with that outdoor compressor underneath your bedroom window or right next to where the barbecue is at on the back patio, do you really want it to be the noisiest compressor you've ever heard? Or would you rather it be small and rather quiet? I think we all know the answer to that. So our larger compressors can be noisier. And then oversized systems are going to struggle with that ductwork. We just talked about this, and we're going to talk about it again later. And if you've ever learned anything from live and online trainings, if you hear something mentioned 3 or 4 times every hour, that's probably a good indication that it's worth tracking. So the types of load calcs themselves matter, the types that we do. There's a lot of different ways we can do load calculations. I'm going to show you a few of them. They matter because they each have a different degree of how replicatable and how reasonable they are. And that's what we're looking for. We're not looking for perfect. There's no such thing as a perfect energy model. All energy models are wrong. Some of them are useful. We want them, if they're replicatable and reasonable, they're very useful to us. So we want to think about the application, the type of backup heat, the goals of the project. All of that will factor into the type of load calcs we want to consider. The two most common are block load and room by room. Now, block load, it's taking typically either the whole house or each floor of the house, and it's treating it as one zone. So it tells you the heating loss and heat gain for either the entire house or for each floor of the house. This is a pretty accurate way for whole house systems. It can be fairly accurate. It works great for ductless heat pumps. It works great for simple box-on-box homes. And it works great for homes without huge comfort problems. It's faster and easier than room by room. It does provide the necessary data to size our systems. We have shorter and cleaner reports. It meets Platte River Power Authority and Excel and many of the other utility programs. It meets their base requirements to do this work. And it works with MeasureQuick and the Pacific Northwest National Labs quality installation tool. On the other hand, the room by room is accurate for both the whole house and for zoned systems. So potentially if you know you're going to treat the basement or the top floor or the master bedroom differently, or all of the bedrooms differently, room by room is a better way to go. It's often required by code jurisdictions in new construction, not always though. It does provide all the necessary data. We like that. It also meets all the requirements for Platte River Power Authority and Excel and all the other major utilities in the state of Colorado. And not only does it work with MeasureQuick and PNNL's quality installation tool, it's also a really good thing if you're choosing to do the ASHRAE 221 quality standard, because that requires that you actually have a known airflow out of every register and you measure and compare to it. So it's a great system for doing that. It does take more time and it takes more effort. So it's always going to be a balancing act of, do I need a room by room analysis or am I okay with a block load? I would say you need room by room if you have serious comfort issues, particularly in certain rooms only, if you have serious indoor air quality issues, particularly in certain rooms only, or if your code jurisdiction requires it or you want to do zoning for the house. In those scenarios, room by room is absolutely the way to go. For most standard swap outs, particularly ductless or variable capacity ducted systems without major comfort and indoor air quality problems, a block load is usually going to suffice. Here's a decision matrix for the different types of load calculations that you could do and when they're most appropriate. I'm not going to read everything that's on the screen, but block load is good for most scenarios because you can typically get enough information with or without an energy audit to complete a block load. Room by room, again, it's the right option for homes with IAQ and comfort issues. BPI compliant audit software, it's basically doing a block load for the whole house. You'll miss some of the granularity of being able to do it floor by floor. And you do need to do an energy audit typically to do this. So it works for some, not for all scenarios. But if you're looking at participating in an IRA program or another program that requires an energy audit with BPI compliant audit software, you can use that as a basic block load. Now there are a lot of different pieces of software out there. Some of these tools actually have manual S or something similar built into them. HVAC sizing tool has a very rudimentary version of Manual S built in. The RightSoft and Elite software both have they actually have pretty decent versions of Manual S built in. Conduit Tech does as well. But you can see here there's a lot that are ACCA approved for Manual J and some that aren't ACCA approved yet, but they're ACCA equivalent to different versions of Manual J or Canadian standards. All of these are pretty darn good tools. You can get pretty good at doing load calcs with any of the tools you see on the screen here. It's worth looking into if they also do the Manual S, which is the sizing and selection component. If they don't, that's okay. Manufacturers actually have, through their distributors, tools that can be used that are specific to their brands, that are equivalent to Manual S. And then I'm going to share with you in a little bit a different way to think this through, which is to understand the parameters of Manual S for sizing, and then using a different tool, NEAP's Advanced Sizing and Selection Tool, for selection. So hold on to your horses. We've got a lot still to go through, and we're just getting to the fun stuff. So next up, we're going to talk about the overall designing for the heating load or the cooling load and what that means, what's the implication for making each of those choices. Next up, we want to talk about when we want to size to the heating load versus size to the cooling load, because we've done a load calculation on the house. And as we saw on the previous one, and as you've seen me indicate, we may have a heating load that is twice the cooling load. So if I size to the cooling load, I'm clearly not going to be able to get all of my heating done. If I size to my heating load, I might be way oversized on my cooling load. Don't worry, we'll address those strategies a little later. But just making this decision, if the auxiliary or backup heat is less expensive than the electric heat, per MMBTU or per unit of energy delivered, then it typically makes sense to size to the cooling load. Or the scenario where they're keeping their existing furnace and they're just going to replace the one-way air conditioner with a two-way air conditioner, aka a heat pump. By the way, when they do that, we typically refer to, especially if the furnace is propane or natural gas or something like that, we refer to this as a two-way air conditioner that is dual fuel. One of the reasons we do that is that's a very accurate way to describe it, instead of calling it a hybrid furnace. Second, words like hybrid and heat pump have been politicized. Unfortunately, there are a lot of people that their brains just shut down the minute they hear those words. But a two-way air conditioner that is dual fuel is a different story. So we want to size to the cooling load if they're keeping their existing furnace and we're literally just replacing the air conditioner with a outdoor compressor and an indoor coil, and we're going to leave the furnace and air handler as is. Or if they want to do an upgrade with everything, but they want to keep that lower cost supplemental or auxiliary heat in place. This is applicable mostly for dual fuel natural gas customers. However, dual fuel propane can be done this way if you get the right size system and allow it to do a very large portion of the heat. It is important to think and learn what your local programs may require, however, for incentives. Some of the utility and government programs will only provide an incentive or a rebate or a credit if a certain percentage of the load is met by a heat pump, even in these dual fuel scenarios. So pay attention. You may have one that says you must meet 60% or 70 or 80% of the load in order to qualify for X rebate, X incentive, or X credit. So just be aware of that. It is important because that might change the metric that you're trying to make a decision based on if you're really trying to buy down that upfront cost. Okay, if that's when we're sizing the cooling loads, when do we want to size to our heating load? This is fairly simple. We size to our heating load to displace expensive auxiliary heat. Now, displace could mean 70% to 100%, right? But typically, we want to think about, we have expensive auxiliary heat, we want to displace as much of that as possible. When that is the scenario, we want to size to the heating load. Now, sizing to the heating load in a state like Colorado, and I'll tell you in a few minutes some of the other cold climate states, you are likely going to want a cold climate heat pump to do that job. So just be very considerate of it. So this is applicable for propane customers that are doing dual fuel. You may size to the heating load or size to a balanced load, meaning all of the cooling load and as much of the heating load as you can afford to cover with your system. Customers with electric resistance heat, or those homeowners who intentionally want to make a decision to go to an all-electric system, regardless of what the fuel type was they had to begin with. So if someone is motivated to electrify now or electrify everything or do anything like that, really slash their carbon footprint, there is a small percentage of consumers out there. It's not as big a number as we thought it might be. It's probably in the 2 to 4% of consumers range are very, very interested and primarily motivated by this, but you are going to find some of them. When that's the case, then sizing to the heating load is definitely going to be to your benefit. So important notes here, just because you size to the heating load, make sure that you are not oversized on the cooling load, at least not by a ton. Again, we'll get into some ways to do this, some approaches in a little bit. And then remember, variable speed cold climate systems are recommended for these types of scenarios. We'll talk a little bit more about cold climate performance in a few minutes and what it really means. But really, variable speed cold climate systems will do the best at modulating to meet the load of the home, and they've got enough of what we call a turn-down ratio. We'll address this a little bit later as well. The difference between its maximum capacity and its minimum capacity, that the maximum capacity can meet most of the heating load, while the minimum capacity on the cooling side may be within striking range of the cooling load. So we really want to get pieces of equipment like that to do this kind of work. So let's jump in now to talk about the cold climate certifications and the specifications themselves, because this is pretty important if we want to say, prescriptively just say, get a cold climate air source heat pump system to do 95 to 100% of the load. Well, it's really good to understand what a cold climate heat pump system means. Let's start by level setting some terminology here. Now, we're not talking air to water systems here. We're talking air to air and water to air systems primarily. And we're really talking the residential setting. It doesn't mean there can't be cold climate systems in other configurations or in other building types, but really that's our focus for today. So we're talking about residential air source heat pumps. There are two primary types of compressors. Now, there are researchers out there working on all kinds of new things. We're not talking about some of that cutting edge solid state stuff, and we're talking inverter driven and conventional, which is usually single or double speed or single or two stage, you'll hear them referred to as. So they're either conventional or inverter driven. Within this, there are whether or not they are cold climate listed. And there are two cold climate certifications or primary specifications that we want you to pay attention to at this stage. The first is the CEE, or Consortium for Energy Efficiency tax credit level, right? So if it qualifies for the tax credit, and the reason why is that's obviously a nice chunk of money potentially to help buy down first costs. Then there is Energy Star Cold Climate Certified. This is more commonly associated with things like those IRA programs. At the time of this recording, Colorado's IRA programs were still in limited launch for income qualified only. They have not launched publicly largely yet, but this is where we believe most of those programs will land. And then there's always those that are not listed at all. There are other certifications out there. NEEP has a cold climate certification. We'll talk a little bit more about NEEP later. So what qualifies as a cold climate? It generally means that it's efficient at low ambient temperatures and it can achieve capacity, performance, and maintenance. So that's a lot of mumbo jumbo. It means that when it's 5 degrees outside, the system is still efficient, and we say in that case it's 1.75 coefficient of performance, or COP, at 5 degrees, and it's capable of delivering 60 or 70 or 80 or 90% of its full power or its full capacity or its full oomph, even down at 5 degrees. Right? Our systems are rated at 47 degrees. When you see something that says this is a 48,000 BTU cold climate air source heat pump, they mean it's 48,000 BTUs of oomph at 47. If it had 70% capacity maintenance, that means that 70%, or a little more than 2/3 of that, was available even at 5 degrees, right? So that's usually some of the big definitions for a cold climate. I do want to mention that we talked about dual fuel earlier. There are a lot of people who like the term hybrid. There are a lot of people who like the term dual fuel. Either way, they can mean many things. It can talk about the equipment itself and compatibility between equipment, but it can also be a utility program description. So really pay attention on how you use these words. Pay attention to the definitions a utility program might have. You just want to make sure you're saying the same thing the utility is, particularly if there are things like incentives on the line. Now, specifications themselves, not just certifications, can get really wild and woolly. And what I'm showing you here is two of the largest utility programs in Colorado, PRPA's Efficiency Works and Xcel, and they have different specifications. They're also different from the Colorado tax credit, which is different from the federal tax credit. Now, the good news is the Colorado tax credit uses Energy Star, so we can see that over on the far right-hand corner. In 2025, I've highlighted the federal tax credit level because it just changed. They just updated the specs here. Now, if you click on this CEE1 25C heat pump tax credit spec down at the bottom, that will actually pull up the specifications. And what they've done is they've created two pathways. A pathway for dual fuel, which is listed here as a standard air source heat pump, and a pathway for all electric, which is listed here as a cold climate heat pump. Now, some of the things that have changed, they've lowered the EER requirement, the ER2 requirement. It's lower, you'll notice, than, say, Xcel's specification number. And they also lowered the capacity maintenance. Now, while we still think 70, 80, 90% capacity maintenance is a good thing, in order to qualify for the tax credit, for the cold climate or all electric, it needs to be 60% capacity maintenance, and for the dual fuel, it needs to be 45%. The reason why is they're assuming that you're going to be switching over to your backup heat with the standard heat pump or the dual fuel much earlier than 5 degrees, right? That's why they're not as bullish on the capacity maintenance there. But both of these changes, lowering the EER and lowering the capacity maintenance, were done so that more equipment could qualify for the tax credit. That's a really important thing to understand. The goal here is to have more equipment qualify, therefore making it easier for you to sell it. It doesn't mean that these pieces of equipment are going to have an easy time of doing the whole job, but it does mean that more of it will qualify for the tax credit. Now let's take a look at 2026. What's changing there? Well, in 2026, it's anticipated that Energy Star's version 6.2 will be fully adopted. It is available. It was finalized in December of 2024. So at the bottom of the screen, you see it's underlined here, Energy Star version 6.2 specification. If you click on that in the PDF, it will open up. But I've highlighted it here because it is upgrading itself a little bit in 2026 in terms of a future specification. So you'll notice that for this, you do not have an ER ratio for cold climate, but you do have an EER for the dual fuel scenario. So that's something to pay attention to. You will also notice that there's some small changes to the federal tax credit. Primarily, the capacity maintenance is going up, and there's this new thing called AHRI 1380. 1380 is a demand response capability requirement. So as we look at federal tax credit in 2026, the 45% is going up to 50, and the 60% capacity maintenance is going up to 65. And then this new AHRI 1380 is being added into the mix, so it has to be demand response capable. The goal is by 2027 that Energy Star and federal tax credit will be virtually the same thing. So they were further apart in 2023 and 2024. Starting with 2025, each of them is making upgrades moving forward so that these two specifications are more closely aligned in the long run, with that goal again, so that by around 2027, Energy Star version, whatever that will be, version 7, 6.3, what have you, will be very, very similar to the federal tax credit. Now that still may not be the same as your utility program incentives, so you do have to be aware and have to think through, who am I trying to qualify for? If I'm trying to qualify for Efficiency Works, make sure you also get one that has a 10-year, and then you could also qualify for Excel. Or go a little bit better in the SEER and a little bit better in the HSPF, and make sure you qualify for the state tax credit. These are some, it's a shell game and a balancing act we all have to play. The goal is to make this easier by 2027. So keep your head on straight, think it through, take a close look, talk to your consumers, your customers about where they're at, what incentives are available, and you can use this to help guide you towards the pieces of equipment that can solve the most of these challenges and bring the most cost parity to the equation by qualifying for the most amount of incentives, rebates, and credits. Now we're going to move into heat pump sizing specific to Colorado's climate. Before we get into all the details, here's some good news. The Consortium for Energy Efficiency and others have developed a lot of good resources, and I'm going to point them out as we go through this next section. So here, this is a flow chart that you can find on the air source heat pump sizing considerations for heating and cooling. And there's another resource called Air Source Heat Pump Decision Matrix and System Design Guide. Between these two resources from the Consortium for Energy Efficiency, you're going to find a lot of things that can help you have these conversations with your own team and the kitchen table conversation with the homeowner to help them understand why you're sizing and selecting the equipment that you're picking. So I will mention it multiple times as we go through. There's a lot of great resources here, and I really hope that you'll follow up and download each of these from the links that we include. So when we talk about sizing, you're often going to hear people mention Manual S, right? So that's S could be for sizing or selection. Manual J stands for Joule, actually, which is a unit of heat, so it's about the load calculation. Manual S is now the compatriot product from ACCA that helps you size and select equipment. But let's make this even more simple. What Manual S really is a set of bumpers, just like when you go bowling with me or someone terrible, and they just need these bumpers to help prevent them from rolling a gutter ball. That's what Manual S is. It provides you the bumpers or the guide to improve your chances of getting a strike or a spare and reduce your chances of bowling a gutter ball. If you think about it that way, Manual S is just primarily a set of rules that if you follow them, you can size and select equipment to meet the loads for the home. Now, NEEP, who I've mentioned before, the Northeast Energy Efficiency Partnership, they had developed this little guidance here a little while ago, right? And they'll say, general design selection. Selection involves applying the results of the heat and cooling load calculations to the selection of equipment to deliver the necessary heating and cooling in the home. So it's fairly simple. Now they have some equipment capacities right here for meeting cooling only or for meeting heat pumps and heating dominated climates, right? You'll see 95 to 115% for cooling, 95 to 125% for heating dominated climates. This is the older version of Manual S. These were the older bumpers that were in place. So we're going to get into the newer ones in just a second. But if we just remember again, all we're trying to do is select and size equipment to meet the heating and cooling loads of the home. So what are some of the updated bumpers, if you will, the updated Manual S sizing guidance? Well, for single and two-speed heat pumps, you can go to 120% of the heating size limit and 120% of the cooling size limit. So if something is, you've done the Manual J load calcs and it says you need 47,000 BTUs for heating, you could then size to 120% of that. Now, if you're going with variable capacity heat pumps, particularly in an advanced dry climate like Colorado is, you get a little bit more flexibility. And the reason why is due to the variable capacity nature of this equipment, that ability to ramp up and ramp down to try to load match what is happening in the home. And it is important to say that the limit is in reference to the design loads of the building. So for the advanced climates, it's 150% with variable capacity heat pumps of the heating design load and 130% of the cooling design load. There's an alternative to manual S out there, and it's one that I like a lot. If you are working in an area that doesn't mandate or require manual S, I actually find the Canadian NRCan's Air Source Heat Pump Sizing and Selection Guide to be just as good, if not better. Now, within these guides, there's typically what's called a normative and an informative component. The normative is the rules, right? Whereas the informative helps guide you to applying the rules. What's available currently with the new Manual S is only the normative. Now, depending on when you're watching this video, where it's expected sometime in mid-2025 that the informative component would come out as well. At that time, you'll be able to purchase the entire Manual S for download. The Canadians, their guide here, and it's NRCan, stands for Natural Resources Canada, they've kind of combined the normative and informative into one, actually two documents. And these two documents both have the rules as well as a lot of guidance on how to apply the rules in their documents. So this is an example of how they organize the sizing and selection process. For the Canadians, it's based not just on meeting the loads of the home, it's based on meeting the client objectives or goals for this air source heat pump installation. So it doesn't really matter which one you use unless you're in a jurisdiction or participating in a program that specifies one or the other. I personally really like the NRCan sizing guidance. I'm very interested and excited to see what the new informative components of Manual S bring to the table. It may change my mind and swing me to more of the Manual S side. But for now, either one is going to work very well. So those are the initial goals, right? Creating some bumpers and some formulas that help you think this through. But I like to think of design to include what's the application? Are we sizing for heating or cooling? So is this a dual fuel system, an all electric system? I like to think about those limits that we talked about, but I also do want to add in the goals of the homeowner and of the project. And I want to consider things like humidity as well when I do this. So I think of new goals as this kind of formula of I take an existing set of rules. Stimulus is provided to me, so I try it out on a number of different projects. I talk to contractors, I talk to manufacturers and distributors and homeowners. That is all new stimulus for me. As I get new stimulus, I'm able to look at data and create a new response. So the new response is going to be my own approach to design that is a combination of what you see in Manual S, in the NRCan guide, as well as some additional guidance that you really have to tease out from those other products. Really specific to things like humidity control, to the variable nature of a variable capacity heat pump, to whether or not which type of short cycling you want to pay most attention to. And so this is going to be my little section with my new goals, trying to fold in the best of what I've learned over the years from Manual S and from NRCan. So I'm going to start by looking at climate zones. Now, I'm going to show you 4 climate zone maps. The first one is the official one. I'll have a couple of them that are kind of jokes, but you might find them to be helpful, at least the second one, in talking with homeowners. And then the last one is a newly developed set of climate zones that takes into account not just the climate in terms of average heating and cooling degree days, but also elevation, exposure to wind, whether it's a dry climate or not. So it takes all of that into account, and it also looks at things such as how rural is the area, how common is it with its population density. All of those things get factored in. So let's take a look at these 4 as we go through. The first, this is known as the IECC climate zones, sometimes also the Building America climate zones. Building America added this white line, the warm, humid line, to the IECC climate zones. Most of Colorado is all of Colorado is in the dry climate. Most of it is in climate zone 5, 6, or 7. And those are all considered cold climates. You got a little corner in the southeast that is in climate zone 4, which is considered a mixed zone. So it's a mix of cold and a mix of warm. That is a tiny fraction of the percentage of people that live in Colorado. So this is how you would do it based off for, say, energy codes, things like that. It's usually going to be prescribed with this climate zone map. But let's face it, no homeowner knows this climate zone unless they happen to be an energy geek. So a different way to look at it would be, are we in a cold climate or not? How much snow does it take to cancel school where you live? If it takes 6 inches or more, congratulations, you are in a cold climate. Now, isn't it interesting how the 6 inches or more aligns with climate zone 5, 6, and 7 on these two maps? It's very interesting how closely those align. So for that homeowner, it's a way to have that conversation with them. Hey, if it takes at least 6 inches of snow where you live to cancel school, then you're probably in a cold climate. Let's treat it as such. Now, more on a pure comedy level, my buddy Bruce uses this one, and we put this up sometimes just to help people who think it through. Like, there are some parts of this place that are unusually cool, some parts that are cold, and some parts where it's just, how in the world do people live like this, right? So I put this in often just to get a snicker out of folks. It's not an official climate zone map, but it's one I love all the same. Now here's the newest one, and this is from Dr. Jeremy Posadas, who, like I said, took into account all the components of climate, not just how cold and hot it is, but also things like altitude, exposure to wind, and dryness, as well as how rural areas are, and it lumped them together in areas that are more similar. I'm going to use this one for today. I could also use the first one, but this also gives me the chance to use the term Appozarca, cross between the Appalachians and the Ozarks. But we're looking here in Colorado mostly at Mountain West and Great Plains experience. So Colorado Springs and Pueblo and maybe Fort Collins are considered Great Plains. But Denver and Aspen and Gunnison and a lot of our other places are really truly going to be considered Mountain West. So just think about that as we move through. There are other ways to look at it. This is these are heat maps from something called WeatherSpark. It's another good way. I use this often if I'm going to compare research from one climate area and see if it would apply to another. What they're doing here with these heat maps is they're categorizing how much of the average hourly temperatures, and here I compared Fort Collins, Aspen, and Pueblo, and how much of the time of the year and the time of the day is warm versus comfortable versus hot versus cool versus very cold and cold versus freezing and frigid, right? Now, if you look at Fort Collins and Pueblo, they have a very similar heating load and a very similar cooling load. But if you look at Pueblo, it's got a lot more time where it's hot than you have in Fort Collins. Because of that, this down at the bottom, you see the heating load to cooling load is a little lower than it is in Fort Collins. Now, in both cases, in all three cases, it's way above 1.5. In fact, it's above 1.75, that ratio. But it is important to be able to look and compare. Now, if I look at Aspen and Leadville area, I mean, there's very little time where it's warm or hot, right? We have some comfortable time, and we've got some definite frigid time. Because of that, the heating load, the needs when it's time to heat, is 3.2 times the cooling load. That is a dramatic change, right? So that is far much more heating load than cooling load. Just important to think about some of the rules and things we're going to talk about. Consider how close to 1.75 these numbers are. The further the heating load to cooling load is above that number, the more dramatic your options are, and the more likelihood you're going to need to make more than one selection from my proposal. Now, I use the HVAC sizing tool. We talked about this a fair amount in the other seminar, right? This is a free tool. It is much more like a traditional Manual J software. It's accurate to Manual J version 7, not version 8, but it is a very good tool. Once you get good at it, you can do a house in about 30 minutes after you've already collected the data. It might take you 30 minutes to an hour to collect the data. So, you know, you're looking typically at an hour and a half to 2 hours all in with this tool, which is a little bit faster than some of the other tools out there. Just using this to show, and here's our Fort Collins in the upper right-hand corner, right? 49,000 BTU per hour for heating and 24,800 for cooling. We're also going to share this tool with you today, the NEP tool, the Northeast Energy Efficiency Partnership. And this tool is part of a database that allows you to look up products and look at extended performance tables of various products that meet some minimum requirements. It has some extra search functionality. If you look here, potential eligibility for IRA tax credits and Energy Star certified. These are filters you can use to make sure that only products that meet those specifications show up. So really good tool as a product database. But it also has, if you see at the bottom, this advanced search size for heating and cooling. It does some pretty advanced things, and there's a brand new user's guide. I highly recommend reading this guide and downloading it and keeping it on your laptop or your tablet. This guide, I helped write the original version of it. The new version is so much better. And it's not just for using this tool, although that's its primary use case. It also walks you through why a lot of the different metrics that we talk about with sizing and selection, why they're important to the decision making. So it's really an all-around great tool to use. Again, I highly encourage you to download this and keep a version and read it. It turns out the NEP tool has also been updated in the last year. So if you want to watch a webinar, if you know, read that manual, but if you also want to watch a webinar to see how other people use this tool, you can either scan the QR code here or click on this link when you get the PDF, and there's a recorded webinar that'll walk you through how to use the tool, including some of the brand new updates that have been built in the last year. So one of the things you're going to get with the advanced sizing tool, once I've placed in the heating and cooling loads and put in the zip code for the area I'm at, it's going to generate a bunch of charts for me. And what these are helpful for is going to be to look to see how well is the equipment I'm selecting going to match or meet the needs of the home. So what you're seeing here is I've stripped out all the performance of a selected piece of equipment, and I'm just looking at the needs of the home. The vertical yellow line on the left, this is the heating design load. On the right-hand side is the cooling design load. And then the blue bars, these are what's called the load times the hours. So this is the annual heating or cooling load times the number of hours at each of these temperatures, outdoor temperatures. And if you look here, by far and away, the load times the number of hours it will experience that is greatest between 17 degrees and 94 degrees. So this is the range that we really want to see any heat pump we select performing very, very well. Now, every house is going to have a slightly different one of these maps based off of the heating load and cooling load. It's been calculated in Manual J and the zip code that you've selected. Then you'll get to apply on top of it the performance charts of the selected equipment. So again, this is a very great tool in my mind to help understand at what temperatures does our piece of equipment need to perform very well. So the other side of that equation is the performance data that you get from the various pieces of equipment. Here's a random piece of equipment I selected. What it's showing me is the dark red line at the top is the maximum heating load. So between 47 and negative 13 degrees, this piece of equipment has reported data that was tested at 47, 17, 5, and negative 13. And what it's showing me at the top is the maximum capacity at each of those temperatures. And then the lighter reddish orange is the minimum heating capacity. The two bright red dots are the rated capacity. So if I look at it and it says this thing is rated 40,000 BTUs, that's what it means, 40,000 BTUs at 47. Turns out the maximum capacity for a short amount of time is actually higher than that for this piece of equipment. It does the same for the cooling load, right? We have a maximum, a minimum, and a rated cooling load. Something else that's important is something we call the turn down ratio. I've mentioned this before. The turn down ratio is the ability for the equipment to operate between its maximum and minimum, to turn itself up or to turn itself down in that range. And the turn down ratio is measured at 47 degrees and sometimes at 82 degrees. I like to average the two. So here, if I look at 47 degrees, the maximum capacity is 48,000. The minimum capacity is 11,000. So this is a little bit more than 4-to-1 in turn down ratio, right? Because it's more than 4 times higher at the maximum than it is in the minimum. Everything between the maximum and the minimum is the Goldilocks zone. This is the area where the equipment is best suited to match the load of the home. Over on the cooling side, we could look at 82 degrees and say, well, the cooling capacity maximum at 82 is around 42,000, and for the minimum, it's right around 15,000, right? So that's close to almost 3-to-1, about 2.8-to-1. If I average those between the 2.8 and the 4.2, I get about 3.5. So in my example, I would say this has a turn down ratio of about 3.5-to-1 if I do heating and cooling. If I looked at just heating, it would be about 4.2-to-1. Hopefully that makes sense to folks. Turn down ratio is pretty important. I happen to randomly pick a piece of equipment here that has a really good turn down ratio. A lot of pieces of equipment have a turn down ratio of only about 2-to-1. And the reason why turn down ratios aren't better is the way that equipment has been invested in order to have better capacity and efficiency at low temperatures, down at 17, at 5, and at negative 13, is they have to give up something in order to make those gains. And some of what they give up are things like the ability to dehumidify houses and the turn down ratio. So this happens to be a really great piece of equipment that both has good capacity and probably good efficiency at these different temperatures, but it also maintains a good turn down ratio. Another critical piece to understand are switchover temperatures and balance points. So when we have a dual fuel system, we literally switch over at some point from the electric heat pump to the backup heat. This is true with dual fuel. So when the backup heat is a furnace of natural gas or propane or home heating oil or wood or coal or what have you, that's where we have a switchover temperature, because literally you cannot run the gas furnace at the same time as the heat pump. They just are not set up to work that way. The reason why is the gas heat exchanger comes before the heat pump coil in that airstream, and when you set it up to run this way, you're putting really hot air post the furnace heat exchanger directly into the evaporator coil for the heat pump or the heat pump's heat exchanger. That can actually make the heat pump not work very well. So you actually have to switch over. With all electric, if you have electric resistance heat in an all electric heat pump, the electric resistance typically comes after the heat pump coil, and it's fine to add extra heat afterwards. So with this, the thermal balance point, or sometimes we call it the capacity balance point, is at the point at which the heat pump can no longer, its capacity, that top line of the previous graph, isn't enough to keep up and match the load of the home anymore. And so at some temperature, as it gets colder, the heat pump literally cannot do the job anymore. That is a thermal or capacity balance point. If you had a dual fuel system, you would have to, right around there, switch over to the supplemental or backup or auxiliary heat. The next one is called the economic balance point. And this is a switchover temperature where we switch from the heat pump to our supplemental heat because it's more cost effective at that temperature to heat the home with that supplemental heat. So with a natural gas furnace, that could be anywhere from 25 to 40 degrees in a lot of cases. But with a propane furnace, that might be anywhere from 5 degrees to 20 degrees, right? Because propane is so much more expensive for a unit of heat. This relies a lot on, yes, the efficiency of the equipment, but also on the primary and backup heat fuel costs. And then finally, there's the comfort balance point. Now, this is the most, or the least specific and scientific of these. And the reason why is comfort is something that everyone experiences differently, right? So what is comfortable to me and what is comfortable to my wife and what's comfortable to our cat are three very different temperatures. So what a lot of people will do with the comfort balance point is they'll either experiment with the homeowner and they'll switch it over after 6 months or after a year to better align with the customer's experience. But more commonly, what I'll see contractors do is they'll calculate the economic balance point, and then they'll just set the thermostat or the switchover temperature a couple of degrees warmer than the economic balance point, and they'll call it the comfort balance point, saying we're taking advantage of the economic equation, but we want to make sure we switch over before it gets, the air delivered temperature gets too cold. There is an alternative to this. Instead of basing it off of the outdoor temperature or the temperature at the thermostat, you can also use a supply air temperature sensor connected to the control board, and that will say once the air temperature in the supply ducts drops below 90 degrees or 88 degrees, at that point in time, we're going to turn the heat pump off if it's a dual fuel system and turn on the backup heat. If it's a all-electric system, we'll start feathering in the electric resistance heat. Right? That's a different way to approach this. It has to do with supply air temperature, not the temperature at the thermostat or not the temperature outside. Okay, so let's take all of this together. Let's start painting a picture. So what do you do when the heating load is 1.75 times the cooling load? Because remember, at this, it's going to be really hard to get a single piece of equipment by itself that does all or most of the heating load without being oversized for the cooling load. So the best options here for a dual fuel scenario, remember, we're sizing for cooling, is we're not going to worry as much about how much of the heating load we're getting. Again, you may have a utility program or a tax credit program that says 70% or 80% of the heating load must be met. So it's a little trickier there. When you have something like that, probably pick two things from these options. If you're just trying to get the basics, pick one. My favorite to pick is going to be to right size as best you can for a dual fuel system in this scenario. Let the heat pump do the work for 6 to 10 months out of the year, and don't worry about it. Let it switch over to the secondary or supplemental heating system at, when the capacity just isn't there anymore. You can do this with a two-stage system, a variable capacity inverter system, or a cold climate system. It's probably the most cost-effective just to use a variable capacity or two-stage piece of equipment and not have to worry about all the cold climate specs. But you may not hit that 70 or 80% threshold for utility incentive, so just pay attention. You can also try to pick a premium heat pump, one that has great capacity and efficiency at 17 degrees, 47, and 82. Because remember, that's where the majority of the time is, right? So picking one that performs really great in those scenarios, has a really good turn down ratio, and a high efficiency there, that's going to really help you in terms of your energy bills and the perceived performance by the homeowners. You could also consider preconditioning any intentional ventilation air. So when you have these scenarios in very dry climates and in very wet climates, you want to potentially either humidify or dehumidify that air, or try to transfer moisture from inside to outside air streams potentially. And one of the ways we can do that is to use an ERV, an energy recovery ventilator. So this ventilator takes out a prescribed amount of air and puts in the exact same amount of air. So it's a balanced ventilation system for the house. When it does that, it transfers some of the heat through the heat exchanger. So if you're exhausting 80 degree air or 70 degree air and it's 30 outside, the incoming air will not come into the house at 30. it will transfer, let's say 70%, 75% of that heat. So the incoming air is now maybe 60 or 65 degrees. So it makes it a lot easier on the heating system and on your energy bills. The ERV will also transfer a percentage of the moisture from the airstream. So it won't actually blend the streams, but it has a mechanism inside the ERV that allows moisture to migrate from one airstream into the other. So that's an ERV. An HRV works similarly, but no moisture transfer. So again, very dry climates, very wet climates. ERVs are probably what you want, unless the house is incredibly tight, like lower than 1 air change per hour at 50. It doesn't seem to make much of a difference there because there's so little natural leakage. You're not as worried about it. You definitely can look for systems with a very small amount of low load short cycling. That will be helpful in the performance of the equipment. And when you size to capture the cooling, make sure there's a 10% buffer below the cooling load of the home and the minimum capacity of the equipment. And we say that because the capacity for the equipment is not always in real world scenarios quite as good as it is when it's lab rated. So we want to make sure we have enough of a buffer there so that we can meet that cooling load between the maximum and the minimum performance capabilities of the equipment. So pick one or pick two or pick three of these depending on how much larger the heating load is than the cooling load for a dual fuel system. So here we're going to look at a couple of examples using that NEAP tool. Now here I've toggled on almost everything, right? I've got how much supplemental heat I'm going to need. That's the pink triangle on the left here. The gold zone is the Goldilocks zone. That's the modulating heat pump range in heating. And in light blue, it's the modulating cooling range for the heat pump. We've got the maximum capacity and the minimum capacities, the red lines. The blue lines, maximum and minimum cooling capacities. This orange line that turns green for a brief amount of time, that is the heating load of the building. Where it's green, those are the outdoor temperatures where the heating load of the building can be completely met by the heat pump, right? So again, we want that green line to be covering as much of those blue bars as possible. On the cooling side, the same thing. Now you got these other little triangles, kind of this orangish red on the cooling side and this yellowish green on the heating side. This is representing how much low load cycling I'm likely to have. You want that to be not you don't want that to be too high. 30% is a good benchmark, but sometimes it's just really hard to get equipment that does that. So if you remember right, we had a heating load of around 49,000. So I picked a 4-ton AirQuest heat pump, centrally ducted, and I looked at this to say, how is this going to do? Now, I love looking at these charts. These are very helpful for me. This is the way my brain works. I can see performance in these charts. Some people don't work like that. Their brains, this is overload. It's too much. They prefer to see this in a different format, right? They want to see it in a table. So here's that same 4-ton system, looking at the product size for heating and product sizing for cooling. And we're looking, and I've decided to highlight and put some green boxes around some of the more important elements. The capacity balance point, if you go back a slide, you would have seen that's where the load met with the capacity. It's telling me around 40 or around 20 degrees is when the heat pump can no longer meet all of the heating load, right? So that's the thermal balance point, the capacity balance point. But this particular piece of equipment is able to meet 86% of the heating load. So if I'm in a program that says I need 70% or 60% or 80% of the heating load to be met, I can use this chart right here to prove that this design is designed to do that. This also tells me this would need about 427 hours of supplemental or backup or auxiliary heat. And it's going to tell me that in my heating load, about 18% of the time, I'm going to have low load cycling. That's well below 30, so I'm okay with that number. I look over the cooling side. The good news is I'm meeting 100% of the cooling load. I needed to do that. But look at this, percent of annual load with low load cycling. Almost 70% of the time, I'm going to be oversized for cooling. I'm going to be cycling on and off. Now, if you remember back to the picture of Fort Collins, we don't have a ton of hot time, but we do have a lot of warm time in Fort Collins. You know, is this going to be the end of the world? Probably not. But it is important to understand what I'm giving up in order to get that 86% heating load served, right? I'm giving up some low load cycling on the cooling. It's going to be a little bit higher than I want it to be. I'd like that to be 30% or less. So I may have said, hey, what if I tried a 4.5 ton system? Maybe that'll lower my capacity balance point and get me closer to 90% or something. So let's look at that. Here's the 4.5 ton version of the same piece of equipment, right? But look, now my low load cycling is red for heating and cooling. So I'm not doing, and the amount of my heating load on the load line that's covered between the maximum and the minimum, it's a shorter green line. I don't know that this is better. I think this actually might be worse. Yeah, my capacity balance point went down a little bit. My percent of annual heating load went up a little bit. But now I've got 39% low load cycling and heating and still almost 70% low load cycling and cooling. So bigger was certainly not better here. If I had gone down to a 3.5 ton or 3 ton piece of equipment, I may have found that I was still able to get 70% of the heating load, and I might have had a much less percent of annual load with low load cycling for cooling. All right, what about if our heating load is 1.75 times our cooling load, but now we want to go with a cold climate air source heat pump delivering 95 to 100% of our heating load. So again, this might apply for people who are trying to electrify their homes, or for those people that really want to qualify for the maximum tier in a utility program where they say, I want to try to get as much of the heating load as possible. Most programs will accept 95 to 100% of the heating load. So what can we do? Well, I have 4 options. I can look for an all-electric cold climate heat pump rated Energy Star or CE1 and look for one that's got cold climate variable capacity heat pump and for an awesome high capacity maintenance. That's going to ensure that I really nail that 95 to 100% of the heating load. But if I do that, think about what my cooling load might be like. So I might pick as my second one here to weatherize the building. If I can get my heating load and cooling load to be closer to each other, boy, that's really going to help that really awesome heat pump do both jobs very well. Now, an interesting approach, number 3, and I do see some advanced heat pump contractors do this, because it's a little bit hard to have this conversation with homeowners sometimes, is maybe you want to mix and match a couple of different heat pumps in the home. Maybe you want to address the top floor of the home differently from the main floor and differently from the bottom floor. So you could have a mix of ductless and ducted short run or mini ducted systems, each designed to address an individual floor of the home. This can allow you to meet those loads better per floor. And by thinking about it this way, yes, there's going to be some interactions between these pieces of equipment, but good news, in the NEAP tool, you can actually stack multiple pieces of equipment together to ensure that they'll meet the whole home's load. So that might be an approach for a more advanced contractor to really think about this. And again, we really want to pay attention to short cycling and make sure our minimum cooling capacity is lower than the cooling design load. So these are our 4 options. I'm picking probably 1 and 2 most of the time if I want to make this work. So let's take a look at some examples. Here I picked a Midea piece of equipment. Now, I picked a 60,000 BTU piece of equipment, even though my heating load was 49,000. I really wanted to make sure, right? I have a very average 66% capacity maintenance. That's fine for the CEE1 tax credit level, but is that actually going to do the job for me? Well, if I look at my graph up above and my table down below, you can see that with this, I mean, I'm able to get 92% of my heating load here. And I don't have a lot of low load cycling on the heating side. In fact, it looks really pretty decent on the heating side. But the cooling side, boy, I got a lot of low load short cycling there. And really, I'm only getting 92%. This probably is not going to qualify for that top tier incentive for a lot of utility programs or for a full electrification project. So maybe I could look at a different Midea with the same rated capacity of 60,000, but with a better capacity maintenance. And what do you think I might see? So here's a Midea MDH series. Look at that capacity maintenance, 89%. Still picked the 60,000 BTU system because I really wanted to make sure. Now look at my graph. Well, wouldn't you know it? I look at the graph. Look how long and beautiful this load line is in green. That's all time where I'm in the Goldilocks zone and I'm meeting the majority of the load times hours. That just looks beautiful. Cooling load, I have the same problem I've been having for a while here, right? The good news, my capacity balance point is low. I'm able to meet 97% of my heating load, still low load cycling, but darn it, I'm still at 65% low load cycling on my cooling load. So just going with a better capacity maintenance ratio didn't solve all my problems. It made it look even better on the heating side. Really looks great with my load line being all green, but the cooling load, I haven't fixed it yet. So what could I do? What if I went with a smaller piece of equipment with an amazing capacity maintenance? So here's a Canair product. Now I picked a 4-ton system here, right? It's rated right at 49,000, which is right what our heating load was. But look at the capacity maintenance, 96%. So at 5 degrees, my maximum heating capacity is 96% of my rated capacity at 47. That is awesome. How does that look? Well, I'm at 95% of my heating load, so not quite 100. Still great low load cycling, but look at how much better the percent of annual low load cycling was for cooling, right? The percent of annual load modulating and cooling went up, and the percent of annual low load cycling went down. It's still above 30, but maybe that's just as good as we're going to get without weatherizing the house. But I wasn't here to tell you, if I were able to weatherize this house a little bit or change all the ventilation into an ERV, I might be able to change my heating and cooling loads enough that I'm able to have this great performance on the heating load side and continue that improvement on the cooling load side. So hopefully that is helpful to people to be able to think this through. Again, I prefer looking at the charts up above. That is how my brain works. That's easier for me to explain to a homeowner or to a utility program or a local government permitting office. Other people really like the numbers. That is absolutely fine too. Pick the way that it works for you and get good experience using this tool. The next component when we look at this is looking at the sensible load versus the latent load. Now, on the load calculation side, the loads, we call that the sensible heat ratio. So what percent of the building's cooling load is made up of sensible heat? So sensible heat is what actually changes the thermostat number in your house, right? It changes the temperature on the thermostat from 68 to 72. That is sensible. The latent is what changes the humidity. When we have a negative latent load, like you see in almost every house in Colorado, that means the sensible heating ratio is at 100% or above. So we're able to do 100% of the load with sensible. Now, on the flip side of this is the equipment, and that we call the sensible heat fraction. They actually have a lot of different names for this. I'll go into that more in just a second. This is the capability of the equipment we're selecting. And why this is important is our modern high CO2 heat pumps and air conditioners. They achieve better sensible cooling. And they're able to have that capacity maintenance that they want. But part of what they give up is the ability to dehumidify. Now, we don't care that much about dehumidification in Colorado, but we do just want to be aware that we like sensible heat fractions that are high, which means we want to get as much of that capability out of the equipment, focusing on sensible heat reduction as opposed to latent heat reduction. Why? In Colorado, we simply don't have to worry about latent heat. So we want the highest SHF we can get for our equipment. Ironically, if I were talking to people in the Midwest or the Northeast, Or in Canada, I would typically say, okay, if we're in a climate with humid summers, I want my sensible heat fraction to be the same or lower than my sensible heat ratio, meaning I want to make sure that my heat pump can not just lower the temperature in the building, but can remove the dehumidity, or dehumidify. So slightly different approach depending where we are in the country. Now, there's some other considerations for Fort Collins or Leadville or wherever else we are in Colorado, and that is the altitude adjustment factors. Now, because we are in a dry high climate or high elevation, we're able to use just the sensible capacity and dry coil numbers that you see on the far right-hand side of this. Fort Collins is around 5,000 feet elevation. Leadville is around 10,000 feet elevation. So we need to derate the capacities of the equipment based off of these altitude adjustment factors. So we're going to use this now. Be aware, some manufacturers, they give instructions that say you don't need to do adjustments because that's already been factored into the equipment. So Lennox and Mitsubishi, maybe some others do this. Talk with your distributor about this. Talk with manufacturers' reps. Read up about your products. Watch YouTube videos about them to really learn this, because this can be a big difference, right? We're going to go through and use this formula in just a minute here for a couple examples. So that sensible heat fraction I talked about of the equipment. It's sometimes called the CSHR, or the capacity sensible heat ratio, especially if you know some old timers in the industry. They probably are used to saying CSHR, or SHF for sensible heat fraction, or sometimes it's in the manufacturer's performance tables as the S to T ratio. That's the sensible to total ratio. So in this piece of equipment, the system was rated at 33,000 BTU cooling capacity at that first column, which was probably at a specific total external static pressure and fan speed. So it is saying the actual total cooling capacity is 32,872 BTUs. The S to T ratio is 0.6. So of that, 0.86 of that is sensible cooling capacity. The other is latent cooling capacity. So now if I take the 32,872, I multiply it by my altitude adjustment at 0.92, let's assume we're in Fort Collins, and I multiply it by the S to T ratio, or the sensible heat fraction, it means I'm only getting 26,000 BTUs of sensible cooling capacity out of this piece of equipment. Now, before you get too upset, don't worry, there is a little trick that's going to help us out in a dry climate. Right, so there's 32,800, 0.86, and I did the math. Here's the little helper part. In Manual S, there's this little section that says, after sizing for total capacity and qualifying the latent capacity, the designer is permitted to recalculate the sensible cooling capacity by adding half the excess latent capacity back into the cooling capacity. So if I do this math, right, this was remember we got 26,000 BTU capacity after the altitude adjustment and the S to T ratio. But now I can calculate the excess latent capacity. So the excess latent capacity was 4,602 because 2870 is my total with the 32,000 times 0.86. That, which was less than the 32,872, is 4,602. Half of that is 2,301. I can add that back in. So my rated piece of equipment at 32,872 BTUs is actually an adjusted sensible cooling of 28,309. Whew, that was saying a lot, wasn't it? Now this stuff does not always show up in the NEAP tool. There is a hope that in the future the NEAP tool will allow for some of these kind of maths to happen and automatically adjust the maximum and minimum cooling capacities based off of this. Right now they're just showing you off of the performance tables, so we would have to do this math. So if you think about those examples that I showed you with that kind of big low load cycling component for the cooling, Well, imagine our low load or our minimum cooling capacity may actually be a little lower than it was rated because of all these adjustments. So this actually may work to our favor because we're in a dry climate and we're trying to have less low load cycling on cooling. This could actually work to our favor. But it is worth understanding because technically this is how you are supposed to do the math, right? So keep this in mind. This stuff is not in the NEAP tool just yet, but it is worth understanding. There's some other efficiency considerations here. I mentioned the coefficient of performance earlier. This is different than the HSPF, or heating season performance factor, or the SEER, right? The seasonal energy efficiency ratios. The HSPF is an average seasonal heating efficiency, and the SEER is an average cooling capacity or efficiency. The thing is, HSPF, whether it's HSPF or HSPF2, and SEER2, are designed to express fairly well the efficiency of single and two-stage pieces of equipment. The way that they actually do their calculations, they don't take into account this ability for the modulation, right? The fact that this piece of equipment spends the majority of its time of the year running at medium to lower capacities, that just is not factored in. So if we want to factor that in, what we can do is we can look at COPs, which is a coefficient of performance, and it's given to us at the maximum and the minimum and the rated capacity at different outdoor temperatures. So if I look here and I say, let's take a look at this piece of equipment. My COP at 95 degrees is 2.93 at its rated capacity. At its minimum capacity, it's 3.57. Now, I mentioned earlier, the majority of the time, these pieces of equipment run somewhere between their minimum and their rated capacities. So the actual experienced COP in the house at 95 is probably somewhere between 3.57 and 2.93. If I look at the heating side, same can be said for 47, right? It's more efficient. The COP, coefficient of performance, is more efficient at 47 degrees at minimum capacity than it is at 47 degrees at the rated capacity. So the actual experienced efficiency is likely somewhere between these two if I'm right sized and my equipment can run at low speed for long periods of time. Now when you get really cold, down at 5 degrees here, my COP starts to drop, even at the minimum capacity at 5 degrees compared to the rated capacity. And the reason why is we're trying so hard to get as much capacity as we can, we're giving up some efficiency at those lower temperatures. So this just goes to show you that we need to get these extended performance tables, and this is where we want to look for how this equipment is likely to perform. If we are truly right-sized, we have the least amount of low load cycling we can get, the most amount of coverage between maximum and minimum capacity, the longest amount of the load line within that Goldilocks zone. If we can right-size that way, then we get a chance to look at this equipment and say the COP that we're going to experience is likely somewhere between the COP at the minimum capacity and at the rated capacity. And at 47, where we spend a lot of our time, that number is going to look pretty good. You get down to 17 and 5 degrees, it doesn't look as good. But that is, so look at where the house, the load times the hours, is the highest. And if that is over 32 degrees, and it will be for most homes, then that's what you want to look for in terms of efficiency of the equipment. What is that COP between the minimum capacity and the rated capacity at 47? That number by itself will tell you a lot about the operational efficiency of the equipment. So if you're starting to look at equipment for how efficient it is, look here, not at the HSPF2 and the SEER2 and the EER2. Okay? Those are numbers we have to put on according to the federal standards for testing, but these numbers are going to better express how variable capacity equipment performs. So let's start merging all this stuff together. Right? Remember, we're going to look at the Mountain West and the Great Plains because that describes Colorado. We want to size to either the cooling load or a balanced approach in our area. Now, Again, if it's dual fuel, we're definitely looking at cooling. It may be we prefer a preference for heating load and size to that if they're going with the cold climate air source heat pump for electrification. But in most cases, you want a fairly balanced approach out here. That sensible heat fraction, or CSHR, or S to T ratio, you want the higher number, the highest number you can get. If you're comparing two pieces of equipment, higher is better. Why? You'll be able to recapture some of that loss latent, yes, but you don't want to have to take half of the extra capacity. You want the highest S to T ratio you can get in a dry climate. When we look for efficiency, look at that COP at the minimum and at the rated at each of these temperatures. In the Great Plains, so in the Front Range part of Colorado, look at 17, 47, and 82. In the Mountain West, look at 15, 17, 47 on the heating side. That's going to be able to tell us how efficient this piece of equipment is, particularly if we're starting to look at 2 or 3 pieces and compare them to each other. Should we weatherize these homes? If you're going all electric, the answer is yes, in the Mountain West and in the Great Plains. If you are doing dual fuel, you may not need to if you can get 70 or 80% of your heating load covered by a heat pump sized for cooling. So again, yes for all electric, maybe for dual fuel. For low load short cycling, in the Mountain West and the Great Plains, we really care about the cooling low load cycling, and we want to try and get that number as close to 30% or lower as possible. Sometimes it's not possible to do without changing the loads on the building, meaning weatherizing and paying attention to ventilation strategies. For ventilation air, we either want an ERV or a humidifier added to our ventilation airstream. Again, an ERV does not produce and introduce new humidity. It just takes some of the humidity out of the air being exhausted out of the house and puts it into the air coming back in. In the Great Plains, especially for very, very tight homes, you might be able to get away with an HRV by itself, save yourself a couple dollars over the ERV, particular for really tight homes. Turn down ratio, again, at 47 and maybe at 82. 82, I would say definitely we want to factor that in Pueblo and Fort Collins more than we care about on the western slope. So the Mountain West turn down ratio, we're looking at 47 mostly, and 3 or higher is going to be great. That's going to give us the best capability for this equipment to ramp up and ramp down and meet all of those needs. The Great Plains, something like 2.25, especially for averaging turn down ratios from cooling and heating, that's your minimum that you want to look for. Now, there are some pieces of equipment out there. It's very common in ductless heat pumps. We're starting to see it show up in ducted solutions as well, where they have what's called a dry mode. And that is where they change the airspeed compared to the temperature on the indoor coil with refrigerant flow. And they try to go through periods of time where they maximize the drying capability of the heat pump. We absolutely do not need that in the Great Plains and in the Mountain West. Other parts of the country, it might be worth considering. It is not worth it here. Don't let someone get excited about that bell and whistle. It's not going to be helpful to heat pump sizing and selection in our area. So this is how I like to put together my quick and dirty guidance for what's important on design and sizing. Again, you're all getting a copy of this PowerPoint in a PDF, so you can print out this page by itself if you want, just as a way to say these are great ways to compare pieces of equipment against each other. Now, we're not done yet. We still got a little bit of time, and I want to make sure we talk again about the ductwork, because making sure that we are right sized for our ductwork or making changes to the ductwork to allow the right size piece of equipment to go in is going to be critical. So let's take a look at sizing and ducts. Now, the first thing I'll mention is at CE, we've got some partners, and we are working on a DOE Building America research project where we are looking at a duct assessment protocol. Right now, what you see on the screen is the very maximum amount of duct assessment you could have in a protocol. But we find that this is probably maybe a little bit overdoing it for every experience. So we're going to try to test out a couple variations and come up with a simplified duct assessment protocol. In the meantime, what I've done is I've taken these and I'm putting them into two different protocols, and we'll get to those in just a minute. But first, I want to do some quick math with you and ask you if you think these couple of houses I'm going to show you have a need for a duct assessment protocol. Let's assume we have an existing system in the house with a 60,000 BTU, 90%, meaning condensing gas furnace, and it has a 3-ton air conditioner, right? Which of those two do you think needs more airflow? And if, in talking to the homeowner, you find that the ductwork is capable of cooling the whole house with this existing system, then ask yourself, if I put in a 2.5-ton or 3-ton heat pump, would that ductwork be able to handle it? So let's do this math one step at a time. First things first, airflow in gas furnaces. One thing to note, the more efficient the furnace is, typically the more airflow it needs in order to deliver those BTUs throughout the home. So a natural draft furnace, like an old 78 to 80%er, it needs about 100 cubic feet per minute or 100 basketballs worth of air for every 10,000 BTUs of rated BTU input. 80,000 BTU furnace, right, is going to need, that's 8 times 100, that would be 800 CFM. Induced draft ones, the 80 to 85% gas furnaces with a little powered ventilator in it, they need about 130 CFM per 10,000 BTUs, and then our condensing gas furnaces need about 150 CFM. So if I look at my condensing gas furnace at 60,000 BTUs, I divide that by 10,000, that's 6 times 150. This gas furnace at 60,000 BTU needs about 900 CFM flowing through it to deliver the heat throughout the building. So if the furnace needs 900 CFM, then so does the ductwork in order for this delivery to happen. Let's compare that to a heat pump or an air conditioner. So we had a 3-ton AC I mentioned. Now, yes, I'm using some rules of thumb here, and it's always worth making an alert when we do that because every brand is a little different. Variable capacity equipment could be actually 375 or 425 CFM per ton. I'm using 450 just to make the math a little easier to count and to be a little bit more dramatic. If I have a 3-ton air conditioner and I need 450 CFM per ton, I need 1,350 CFM. So what was more, 1,350 or 900? Right? Well, the AC needs more than does the furnace. So what about the variable capacity heat pump? Again, I said 2.5 tons. 2.5 times that 450 would be about 1,125. So if the existing system had an air conditioner that needed 1,350 and it was capable of delivering the cooling everywhere throughout the house, then a variable capacity heat pump, which at 2.5 tons would need less airflow, and it should be able to fit in that ductwork. In fact, a 3-ton variable capacity heat pump should have the same airflow needs as that air conditioner. It should also fit if the existing system did its job. So always start here. Do the basic math and have the initial conversation with the homeowner about their experience with their existing system. If you learn this, you may not ever need to do a duct assessment on homes with this type of change. This is going to be most commonly describing a dual fuel scenario. So most of the time, dual fuel systems will not need a full ductwork assessment as long as the heat pump is the same size or smaller than the air conditioner. Okay, hopefully that made sense. So now we're going to look at a similar system. It has a 60,000, 90% gas furnace, and it only had a 2-ton air conditioner. We want to size a heat pump for heating first because we're trying to, maybe put a cold climate system in and do 95 to 100% of the heating load. Maybe the homeowner wants to electrify. Maybe they want to get maximum incentives. Maybe they have a very expensive backup heating fuel type. So here, remember that a 60,000 gas furnace of 90% is going to need 900 CFM. And a 2-ton AC, if you multiply by 450, would also need 900 CFM. The problem is a 3-ton variable capacity heat pump, if it runs at its highest speed, which is going to happen when it's coldest and hottest out, it's going to need 1,350 CFM. That is more than the 900. So now we actually need to do a duct assessment to determine, can I put this heat pump on that set of ductwork, right? Now, one option right off the bat, I could put a 2-ton system on and then supplement that in parts of the home with ductless, right? That might work, and that might avoid me needing to do a full duct assessment. But now we're having that awkward conversation with the homeowner. So let's do this assessment first. So here I'm showing you the 2 options for assessing the ductwork. So I took my large list of all the things I could do and I broke it into 2 different approaches. What I call the measured approach and the virtually assessed approach. Now both of these require talking to the homeowner first, understanding how the existing system is performing, and doing that first bit of math of, am I looking to put in more airflow, the same airflow, or less airflow? I'm going to, for today's example, just to keep this moving, we're going to look at the virtually assessed approach. Because this is relatively fast to do. It does not require you to have a lot of equipment other than a tape measure and a flashlight. And so if we can master the virtually assessed approach, then we can move to the measured approach when we need to. So the first thing we're going to do is look up the total airflow needed for our future system. We're going to inspect the ductworks and account for the airflow to each room as well as for the whole house. We'll identify any bad actors in the duct system. Is there a particular duct run? Is there a damper, a connection? Is there a bad filter slot, right? Things like that that could really reduce airflow. And so I want to go through this inspection process. And for homes with comfort and indoor air quality issues that are serious, or if they are trying to go all heat pump with no backup heat, whether that is all ductless, ducted, etc., but their goal is to go no backup heat, then please do both approaches, do the virtual visual and the measured approach, because it's really critical in those 3 scenarios, indoor air quality, comfort, or trying to go with no backup heat, that you get it right. So you need to do both. But for a dual fuel system, or a system where I think it might work because I did that initial math, I'm going to start with a virtual visual assessment. So with the virtual visual assessment or the visual assessment protocol, we sometimes refer to this as register accounting and visual assessment. So let's dive into this. The first I like to do, my buddy Bruce, I'll give him credit, he calls it the Homer Simpson test, right? When I turn the thing on, does warm air come out of the heating grills in heating mode? If I put it in cooling mode, does cold air come out? I mean, that's just good to understand. Where are the supplies? Where are the returns? Is there anything with a closed damper or that's disconnected in the crawl space or has a cat living in it? You know, is a crushed crossover duct underneath a mobile home? Any of those things, we want to figure that stuff out right off the bat, right? So do our Homer Simpson test first. Next, I'm drawing up the house real quick so I know how big it is, 1,324 square feet. I'm going to go through and I'm going to count up all the supplies and the returns. So right here you can see all the supplies. You can see I've got 3 toe kicks under different sinks, and I've got 1, 2, 3, 4, 5, 6, 7 floor registers. So now that I know this, if I know the size of the duct being delivered to each of these, I can estimate the total airflow of the supply side of this system. Right? So I count up my registers. Right? I just counted 7 out there, but let's say I counted and I had 9 total. I would say, are they all open? Right? I'm looking at that. Are they hard pipe or are they flex duct? And how many returns do I have? Why do I care if it's hard pipe or flex duct? Flex duct is not on a prescriptive level capable of delivering the same amount of CFM as hard pipe. In fact, about 10 CFM less for the same size flex duct as you would get for a hard pipe. And I want to know the average size of return because we can kind of use that to estimate airflow through the return. So I'm looking up at this round duct size estimate chart, and it says that a 6-inch duct can deliver about 85 CFM of air if it's a hard pipe. You notice if I looked over here to flex duct, it says a 6-inch can only do 75 CFM. That's that 10 CFM difference that we were talking about. So I'm already in my head starting to do the math. 9 times 85, right? If we do that, we're starting to get an idea of how much air we can supply through the supply side. On the return, now this is again a rule of thumb. This is my buddy Bruce that I've mentioned several times. There's Bruce live and in action in the field. Right? The general rule of thumb is about 2 CFM per square inch of our return grill. So if we have a 3-ton system, we need about 600 square inches of return grill. If I have a 2-ton system, I need about 400 inches, right? So it's important to understand that these are rules of thumb, but they're helpful for just doing that initial visual assessment. So if that's the case, we had 12 runs of 6-inch, all right? So we had 900 CFM capacity if it was flex duct, 1,020 CFM capacity if it was hard pipe. Now, if I have a new system that we want to have 1,350 CFM, does that look like that's going to work on the supply side? It looks like it probably would have worked for 900 CFM, but that's probably not going to work for 1,350. If I look at the return side, right, 16 by 24, that's 384 square inches. At maximum, it's probably allowing 768 to 800 CFM of air through it. That was barely enough. That was probably undersized a little bit. For the 900 CFM, it's definitely way undersized, almost half the need for a 1,350 CFM piece of equipment. So in this case, a visual assessment alone, on top of doing that first math, tells me this is probably not going to work. I either need to go with a smaller heat pump or I'm going to need to make some improvements. Definitely on the return, but maybe even on the supply. So, you know, we always want to look at this. We always want to do this little assessment and have these conversations with our homeowners about the capabilities, not just of the equipment, not just the needs of the house, but the ductwork that's going to help distribute it throughout the house. So we always check our existing airflow needs or a total external static pressure first. Do one of those two right off the point. You may find that this is not a big deal. But you may find that between that, you know, you're a little iffy and you do a register accounting and now you're sure you have a problem, you're going to need to move and do the full measured approach. Also, some of the early bad actors we look for. Here's a great example. The ductwork that you see in this picture actually looks pretty good on the return side, right? It's a nice big wide return. It's not a sharp turn. It's a nice sloping turn into the bottom of the air handler cabinet, but it has a 1-inch filter. Now, a 1-inch fiberglass filter doesn't have much resistance, but heaven forbid this person reads something about air quality and they put a 1-inch pleated filter in there. A 1-inch pleated filter is going to cause a large static pressure increase and can really reduce the airflow. So if you see a 1-inch filter slot like this, have that conversation with the homeowner. If they're interested in indoor air quality, go to a 2 or 4-inch filter instead, a pleated filter, because they're going to have a lot more surface area and they're going to have a lot lower impact on static pressure in the duct system and a lot less resistance to airflow. In fact, we're actually getting to a point where a lot of filter brands are starting to record their pressure drop on the filter itself. So usually around the edge of the filter or on its wrapping, it will actually have that number a lot of times. That's really helpful to us because we can see how much that factors into this whole equation. So sometimes the answer is duct modifications will need to be made. Sometimes the answer is put a smaller heat pump in and then supplement with ductless in other parts of the home. It's okay if that is your answer. Just have this honest conversation with the homeowner. Hey, going to an all-electric heat pump here instead of a dual fuel means that we're going to have to do one of a couple of things. We're going to have to lower the load in the home so I can put in a smaller piece that matches your ducts. I'm going to have to make adjustments to your ducts, or we're going to have to get really clever with a hybrid mix of ducted and ductless to really satisfy your home. When you put it that way and you talk about how all of these things are connected. You are presenting a set of solutions to a homeowner that your competition probably is not. This makes you a true comfort advisor to that homeowner, and that is a winning formula. So please don't forget, when you're doing the sizing, think through all of these components we've talked about, right? Understand the limits of the equipment to the load of the home. Understand the adjustments we make for sensible and for altitude. Understand the choices we may have to make when our heating loads are a lot larger than our cooling loads, and then definitely make sure that the new system, well, for that matter, the old system and the new system, can work with the ductwork present in this house. Put this all together and you provide the winning formula. Now, some more resources. I mentioned several times having conversations with the homeowners, and I know that for some contractors, it just gives you the heebie-jeebies to hear somebody say that, right? You just say, oh, that's my least favorite part of the job, Dan. Check out these resources from the Consortium for Energy Efficiency. 6 of them are contractor-facing, 4 of them are homeowner-facing. These are a great set of resources. None of them are longer than 6 pages long. They all have pictures. They all break it down into chunks and bites of information that are easy to adopt. When you do this, you actually can improve your kitchen table conversation, as well as have some handy references in front of you for some of the decision making that we've been talking about today. So I cannot encourage you more, and I'm only saying this partially because I was involved in writing some of these, but I highly encourage you to download these resources. You're going to find this improves your ability to think quickly and reference the right things, and it's definitely going to help your kitchen table conversations. Next, please read and bookmark this at the Building America Solutions Center. You go there and you look up guides, and you go to cold climate heat pumps, and you check out the scope, the description, the success. Each of those is a different tab, just like you would have on an internet browser. In between all of these, this one web resource amazingly pulls together the lion's share of everything we've talked about in these 2 seminars. Not everything, but a large amount of it is right here for you in one resource. So read it, bookmark it in every single version of an internet browser that you have on your smartphone, your tablet, and your laptop, because you want to be able to quickly get here on a regular basis. And again, you will be surprised how much amazing information you'll find in this one resource that kind of starts to collate all the things we've talked about in the last 4 hours. And that is worth it, if you ask me, to not have to listen to me for 4 more hours, but instead be able to quickly look it up. Please, I highly encourage you to do this. And with that, look at that. We came in exactly the same amount of time we did for Seminar 1, just a little under 2 hours. I want to thank you so much for spending your time with me learning this, and hopefully there was some new things and some interesting things here for you. Feel free to reach out to me or find me on LinkedIn. And again, don't forget, all of those live links are really excellent resources for you to take this information out into the field and really integrate this into your business. Again, thank you so much. It means a lot, and have a great rest of your day.